Oh, okay, A10 chalkboard XOR game. We're given non-negative integers num sub I, which are written on a chalkboard. Alice and Bob, which are very common names in game theory, so I feel like it's going to be a game theory one. Alice and Bob take turns erasing exactly one number from the chalkboard, with Alice starting first. If erasing a number caused the bitwise XOR of all the elements in the chalkboard becomes 0, then that player loses. Also, we'll say the bitwise XOR itself and bitwise of no element is 0. Okay. Also, if any player starts a turn with bitwise XOR of all elements equal to 0, then that player wins. Okay. Return true if and only if Alice wins the game, assuming both players play optimally. Not sure I understand, but okay. Okay, so Alice have two choices: erase 1 or erase 2. And it's 1,000. And each of the number is 2 to the 16. That's actually probably the key thing to know, because 2 to the 16 is what, like 32,000? Oh, 65,000, sorry. I should have known that one. Because that's the number of bits in like a short, right? Sorry, I even said that wrong. It's not the number of bits in a short, but that's like in a short, that's the biggest number. But anyway, okay. Hmm. Man, okay. So Alice cannot win. Hmm. That's fair. I mean, it definitely forces me to think about stuff for sure. Uh, hmm. I think that ending 1,000 is a little funky. Like otherwise, I would have some way of proof forcing it. I think my problem with some of these game theory ones is that sometimes they there's like a really weird catch to it, and I don't have a great idea. Like it makes it less programming-y and more game theory-y, which maybe it's okay depending on who you ask. But I mean, this. I would say one thing, just like in general, the 2 to the 16 makes me think maybe there's a way to kind of brute force it. But not sure I know how to. Maybe there's a way to pre-process these numbers as well. Because, okay. 65,000 and then you have a max. But that also depends on the state of the numbers available, which is also why it's a little weird. But maybe it's not, because you can't like go backwards on it. And the other person is not going to. Well, I think one thing I'm trying to think, first of all, is, well, Is it path dependent? Because you're never gonna. I'm thinking is you're never gonna use the same number twice. I mean, except in this case where we could like remove the duplicates because that doesn't change the game, right? Because there's like an easy proof where you could remove not all duplicates but just pairs of them, because uh, um, because if Alice goes first, then what, and you choose one of the numbers, then if it is optimal, then Bob will just choose the same number, and then you have the same state. And if it's not optimal, then you just lost the game. So there's no reason for you to choose that, or it doesn't affect the outcome of the game, right? And then I'm thinking like something like, okay, let's say you have a number 2, 3, and then no, not 3, maybe 2, 4, and 6. I think there's like a weird thing where like you count the number of bits and then, or like number of ones, and then that will determine like the parity of the game, and you always want to stay within the same parity, something like that, like some kind of like in the NIMS game, right? Okay, well, let's see. So that's the initial state of the game. I think with what we did before too, like okay, even 1, 2, 3, then you could get into a loop. What is the right solution for 1, 2, 3? Oh wait, you can't get into that because if you start on this state, you already win, so that's not a good state to. So you're taking it and making it so you would never be in this state because it would mean you have lost or won that. Yeah. If you start in this state, you win, right? So yeah. So you don't get any weird cycles, maybe. Then in that case, maybe you could assume that each number only gets used once. And then you could do a recursion based off that, maybe. Okay. I mean, I think I'm just gonna play around with coding this out and see how it feels. I have some assumptions that I've been trying a little bit unstated, but I also say probably you're not gonna see this on interview, or at least if you are, maybe if you're like in finance and doing some kind of, I don't know, crazy analytical stuff or something. But I want that for search or for search. Yeah, let's do it that for search. Should be n squared then. Okay, you're right. Okay, let's start with the q is equal to 0. Also, I think the annoying part about this is that I don't generally have a good sense of how hard it is. Sometimes, like the last one, like you look at it like, okay, this is hard. But this one, I don't know, could go either way. Or like, I mean, it's still hard, but just like maybe I know the answer or not is not something I could judge easily. This is a winning state for Alice. Guess it doesn't really matter what number I use. Or maybe win times one, I don't know. I don't know if this is right. That's the general idea, but okay, fine. Okay, 1, 2, 5. Oh, these have two different things. Oh, because you could burn a 0 to be in the same state to change parity. Wow, 0 is a weird thing. I just thought you would just ignore it unless it helps you, but I'm going to cheat a little bit and see if that changes things. Okay, well. I mean, that makes sense, but because you could use zeros to change the parity and then match them afterwards. So that helps you win if you go first. But the other way. I really don't know how to kind of test for this. So okay, good. I don't think I was right. Just I was very lucky. And obviously during a contest, I probably would have submitted it anyway, to be honest, because I have no more bits to kind of, like, I don't know anything about it. But okay. So is this consistent that it thinks it's a winning state, but it's not? Okay, maybe I need an example that's more digestible than this. This one's too easy. Maybe. Yeah. The number that I had. Okay, that's good. Maybe I need a depth first search. Because every time I do this with buffer search, I feel like I have a thing somewhere. So what the hell? So it's the same. Okay. Let me do all the other ones first again, just so I don't swap everything. Yep, so this is still the unique case. Probably stop thinking about it. Okay, so what do I have here? I have 1, 1. So there's no way to get 0 in the middle. And thus you lose. As you pick any number, Alice will be stuck in the last move, which I don't really consider in how I do it. Why is that? Let's take a look. Get to 15. Order one number once at bat. How do I get to 15 and two numbers? Oh, I get to 7 and then 8. That's not what I want to do. Okay. I mean, I think I'm just going to rewrite this in depth first search. I feel like I messed up the formulation with in depth first search. Yeah, let's be careful trying to be cute. Maybe not even need this. But okay, let's go. The next opponent wins. Okay. Otherwise, if that is true, meaning day one, you don't want to do it. And now we cache it. I have to handle zeros, but I guess when n is 0. Oh, not even. Because there's cycles, it's not a. Here's the way I do it, there's cycles. But man, I missed that part when I said I wanted to do an easy one to end the night, but good submission. Yeah. I mean, I think that's the problem with these game theory ones is that, I don't know, like it's not very, eh. It is a fun problem. It's just not an interview question, I guess, which is kind of weird for Leetcode, but maybe not. But thanks for kind of staying with me though. I think to be honest, if I try my thing on a contest, and then I would probably have just given up on this one because I feel like um, game theory game theory stuff is kind of hard and weird. Uh, yeah, but I also feel like game theory is not a thing that I don't know interviews should be testing unless you're like I said in finance or something. Uh, but like if you give me a hit, but hmm, I guess I should have kept the. You probably still need to figure out the XOR at some point. That's fair, but I've used it for like probability stuff, like statistics, but not anything too crazy that I could think about. I don't know. Maybe I have. Oh, I mean, there is that one time where I used dynamic programming to tile tile pictures on a in a pretty way using some cost function. But I did use dynamic programming back in the when I was really into computational biology back in the day. But that was probably like a decade and a half ago. So yeah, thanks. I am trying to still figure out this one first, and then maybe I'll do that one. But thanks. Um, okay, let's break this down. What does it? What does it mean when? What does this number mean? Or whether? Yeah, it's been a while. I mean, I'm not good enough to do research type things. Well, I don't have the patience. I mean, maybe both, but definitely back in the day, I was very interested in it, and it was good. Okay, let's say this is zero. What does that mean? If this XOR of everything is zero, that means like 1, 2, 3. What's 1, 2, 3? I didn't return anything, but expected to be true. Alice goes first, Bob, and Alice goes. Why is that true? Oh, because, okay, well, no, obviously, because if at any point starts to turn with zeros, okay, so if this is 0, then Alice wins, so this is true. What happens otherwise? Yes. But that means that now you can just trying to think about. I guess in this case, we'd never choose the 4 to lose. And then everything else would never XOR to 0. Oh. All right, let's go back to base principles. If man, I don't know if I could prove this. There are pockets. So I'm thinking like about parity, and I think the only, and that's why I have these two examples, is that you could only change the parity if, okay, like let's say you have a length n array. How long have I been doing this for? Yeah, half an hour. Maybe I'm just a little bit tired today. Okay, given n length array, well, the default case is that you just pick alternating ones. And then the last number gets picked. Then Alice wins with its even number, and Bob wins with that. Okay. Yeah, so it's even. Alice wins. Okay. Oh. But I think the thing I'm trying to think is, well, I mean, this is not true, but because I'm thinking about like, so in general game theory, when you talk about like names, numbers, and stuff like that, you essentially have 0 states where, or yeah, 0 states where you're what they call a maximal excluent number, which is called max, MEX for short. So those, the other states for that is or when, I mean, it's explicitly given by the form to be 0, and the only way to kind of change that is to change the parity. But because all those states are losing states or winning states, but they're all ending states, there's no way to change parity, because the only way to change parity is something like 1, 2, 3, where you have odd number length that gets you from a winning state to a winning state. And we have like 1, 2, 3, 4. You'll never lose it, because you never lose because it's even number, and you would never choose the 4. You just choose anything else. That can't be it, right? Is there a way to have 2 sets of numbers that XOR to 0? No, because by the definition of how XOR works, to get to 0, there's only one number that can make that 0, and you just not choose that number. And because if this, I feel like I also spent an hour the other day on a game theory problem, because, and it was like 3 lines of code. So let's see if this works. Let's see if this works with this first. I have this whole list of stuff. Also, I'll be very upset if this is the case, if this works. Even more so than the washing machine problem. Okay. Not happy about this. Oh my god. I mean, I guess it makes sense. I just don't. And even this part is just because it's given to us kind of directly. I hate this problem. I mean, maybe with some hints in an interview, maybe that's okay. But I don't know. I want to do a little bit more programming than this. I think that's the thing. And I spent like half an hour on this, right? I don't know if I have the energy to explain this, but it's, I don't know. It's too much math, maybe. And I love math. I mean, I think it's a fun problem to some degree. Just not necessarily. I don't think I would ask this. Like if I asked this on an interview problem, I would probably hear it from my manager the next day. And like, what are you doing there? And then like, I don't think I could justify it. Let alone, I could be like, right or wrong. They'll be like, I would definitely hear about it. Either they'll be like, Larry, the correct solution is 5 lines of code. You sat in a room with the interviewee for an hour and a half. What were you doing? No way I could justify it. But yeah, I don't know. I mean, I guess my logic makes sense. It's just one of those things where like, how do you convince yourself of it? And that's also part of the, like, I think the other game theory problem that I also spent like a ridiculous amount of time on, it wasn't even quote unquote hard. It was like, it was it was graded as easy. I just spent a long time because I couldn't prove myself that is right? But I'm gonna use this emoji because apparently, I don't know, they finally let me get an emoji, so so I've been using it randomly. Okay, but yeah, I mean, what else is there to say about this problem? I feel like if you're still watching me talk about this problem, you already have your opinion on it. So I'm not gonna say anymore. I mean, it is what it is. I mean, I have some intuition about this. It's just that I don't know. I'm not feeling very good right now. So that's what I'm gonna say about this problem. I mean, I think like you could